In Module 4 of Chapter 11, we're now going to look at the beginnings of the random walk model. This is the model which underlies the stock price movements which, in essence, underlie the assumptions of the binomial lattice. It's often said that stock prices follow a random walk. And what's a random walk? One thinks of a random walk as a sequence of moves where a sequence of, say, plus ones and minus ones, where it's equally likely that you get a plus one and a minus one, as if you were flipping a coin, a fair coin. Every head is a plus one, every tail is a minus one, and if one flipped the coin repeatedly and wrote down the sequence of plus and minus ones, one could imagine a random walk. The terminology random walk, however, comes from the notion of looking at the sum of those plus and minus ones. So if y is the random variable that's a plus one or a minus one, a random walk would really be a sum of those y's. So that after n flips of our coin, we have a random variable zn, which is a sum of n of these y's. And these y's, of course, each one of them could be plus or minus 1, each with a probability of a half, say. And we can think of it as a random walk by imagining graphing z as a function of n. So a random walk, so if I graph that just for a moment, imagine that at time 1 I got a plus 1, at time 2 I got another plus 1. So imagine that my sequence of plus and minus 1s gave me this. So typically a random walk would be, you would see, look like that. One would imagine that these plus and minus 1s were the value at x-axis points 1, 2, 3, 4, 5, and then you simply interpolate, and you get the typical picture of a random walk. Now, a random walk can be sometimes described by Zn, the total of the y's, or by the change in Zn. And we'll see this in the more advanced chapters we'll be coming to in the next few modules, where we might describe how the stock moves by describing where it is at time t, that would be the Zn model, what actually happens as of time t, or we might look at it in terms of what happens between 2 points in time. How does it change going from point 1 to point 2? And either one of them is a perfectly legitimate way to describe how this process works. So here's a better graph of a random walk. And this is a random walk where, again, it's plus or minus 1 with probability a half. And here you can see ultimately there were 500 flips. So there were, this is a graph of 500 flips. And you can see that it has a certain amount of randomness. If you repeated this if you repeated this program, you would get a graph that might look completely different. And you well imagine that every 500 flips of a coin, you would get graphs that looked quite different. You'll notice that it's random, but it doesn't necessarily mean up and down. That you'll see when you look closely that there are periods of time, like here, where it looks as though you literally got a sequence of plus 1, minus 1, plus 1, minus 1. And then you have periods here where you had a run of minus 1s. Or this period here where you got a run of plus 1s. And, you know, random walks can reflect all of these behaviors, and we can write down probability statements of what's the likelihood of 10 flips of the coin producing a head, which would be 10 plus 1s. The idea that asset prices follow a random walk was originally Samuelson's, which comes from the 60s research of his. And the notion of random really is a reflection of the idea that in the marketplace, the markets are pretty efficient, and there are many ways of defining efficiency, but the basic intuition is that information about pricing gets through the market very, very quickly. So because everything is known, it's equally likely that the next piece of information will be positive or negative in terms of its effect on the stock price. So with that idea, it's equally likely, one might imagine, that the stock price might go up or go down, and simply because it's equally likely that the new information in the market, what affects the stock price, could be positive or negative. Also, mathematically, the price after a period of time is the initial price plus the up or down movements. So the model mathematically makes some sense. But you can't identify a random walk itself with a stock price pattern. There are a number of things about it that just don't make any sense. It provides the amount of the randomness that we'd like to see in a stock price, but we wouldn't want to define a stock price as a random walk. And the reasons are, cumulative down movements can be significant, and you could have negative prices. So you wouldn't want a stock price model where ultimately prices became negative. The second point is that if we were looking at stock price movements and we looked at stock prices every week versus stock price movements every month, you would expect the size of the weekly changes to generally be smaller than the size of the monthly changes. In other words, the magnitude of the plus and minus move should explicitly reflect the period of time over which we've observed the move. A random walk, so right at the moment, doesn't give us that. And the final thing, which would be relatively easy to remedy with a random walk, but it's another criticism of a pure random walk, is one expects positive returns on stock. One would like to see that, on average, the stock price process, it grows at some positive real return on average. The binomial model is a variant of a random walk model which fixes these problems and yet still reflects the statistical essence of random walk.